am Hamideh Nouri.
And my name is Ehsan, Eyshi Rezaei, Senior Researchers at Crop Science Department, University of Göttingen, Germany.
Today we are very happy to share parts of our results and challenges in assessing agricultural droughts in global and regional scale in the GlobeDrought project.
I assume we all agree that drought is a global concern. Every day there is an additional 83 million people on this planet, and we expect to reach to about 11 billion by 2100. FAO reports that most serious famines caused by drought. Around 2 billion people have been affected by drought since 1900. 11 million lost their lives. There may not be a way to avoid drought, but we can minimize the damage in most cases. For those of us who are from dry regions, drought is not a new topic. We live with it. All of us have seen numerous cover pages and headlines in different magazines and newspapers about drought, reflecting the importance and extent of drought and how it affects our livelihood all around the world. Here you see a collection of these headlines from different parts of the world. You may know that there are over 150 different drought indicators to map and monitor meteorological, hydrological, agricultural, or socioeconomic droughts to characterize different aspects of drought, including hazard, exposure, vulnerability, and risk. In this project, for the first time, we introduce a composite drought risk indicator and combine 3 pillars of hazard, exposure, and vulnerability for both irrigated and rain-fed crops. In the series of webinars of the GlobeDrought project, we are from the hazard group and only focus on this aspect today. If you are interested in learning more about this composite indicator, please check our recent paper at the NHS Journal. Unlike the extensive number of global and regional drought studies, there are very few studies on agricultural drought at the global scale. These limited studies are mainly index-based assessment, which are often based on remote sensing or climate data that are not usually crop-specific. Limitation of these studies are mainly number of crops that are mostly limited to a few crops, and or spatial extent of the study, which is mainly at the watershed or national scales. The spatial extent of GlobeDrought project is worldwide. However, we zoom in on a few countries like the US, Zimbabwe, and South Africa to have regional assessment. In our global analysis, we use the UN scheme category that divides the globe into 22 segments or regions. This segmentation helps us to present and interpret our results in more details. You see the map and the list of these regions in this slide. We have a semi-automated system to map and monitor historic information as well as early warning system. On the left side, you see drought risk map of the globe over time from 1986 to 2016. On the right side, you see that we categorize the world into different regions based on the UN category. Our warning system shows what we expect to see in different regions as a consequence of drought. In the GlobeDrought project, for the first time, we have distinctive definition of drought and aridity. What we call drought here is a temporary, recurrent climatic feature of abnormally dry weather long enough to cause a significant hydrological imbalance, while aridity refers to long-term moisture deficiency and dryness when the water demand is greater than water supply. In this project, we used three main approaches to assess drought risk and its three major pillars of hazard, exposure, and vulnerability that include remote sensing, modeling, and survey.
Here in this project, we employed a set of modeling tools and remotely sensed information for detection of drought intensity and frequency. The modeling tool for global simulations in GlobeDrought is Global Crop Water Model, or GCWM. The model structure is relatively simple, using the Penman-Montes equation for calculation of potential evapotranspiration. The ratio between actual and potential evapotranspiration is the indicator of agronomic drought in the model. The model inputs are climate, soil, and management information. This model can also simulate the water use and yield of 25 crops at 5-minute resolutions on a global scale. The global model is executed for simulation of drought indicator to check the exposure of different crops to drought on a global scale in the period 1985 to 2016. We found a remarkable difference in intensity of drought influencing various crops on a global scale. It means using the conventional drought monitoring systems which ignore the differences among the crops can introduce a large level of uncertainty to our drought mitigation strategies. In parallel with global modeling activities, more detailed crop models such as SimPlace modeling platform was also used for regional studies in GlobeDrought project. Growth and development of crops such as maize in response to climate and management strategies can be simulated using such a process-based crop models. We use SimPlace for simulation of rain-fed maize growth using different sowing estimation methods as model inputs in South Africa. We indicated a substantial difference among fixed sowing, precipitation rule-based, and remotely sensed sowing estimation methods on simulated drought stress reduction factor. However, the main question is which sowing estimation method can better represent the real field conditions. To answer this question, we tested the relationship between anomaly of simulated yield using the different sowing estimation methods and reported yield at different provinces in South Africa. The results showed that remotely sensed-driven sowing date estimations lead to a better representation of the yield variability in time and space, since it not only relies on precipitation but can also capture the impact of socio-economic factors affecting the sowing decision, particularly for smallholder farmers. In the next regional study, we explored the relationships between simulated drought indicator as output of the global crop model and a wide range of remote sensing indices which used for detection of drought signal. The highest correlations between model-based drought indicator and anomaly of land surface temperature and normalized difference infrared index were detected. The results was relatively similar for different environments including USA and South Africa.
Thank you very much for your attention. If you have any question or comment, please don't hesitate to contact us via email or LinkedIn. Hope to see you in our future webinar series. Bye.